Hi all, and welcome to our first snippet of the freeCodeCamp Smart Contract, Blockchain, and Solidity course. We're going to be going over lesson 0 of the course, which involves absolutely no coding. This is the first section of the 16-hour freeCodeCamp Smart Contract and Solidity course. First, we'll give you an overview of what the course is about, who it's for, how to get help, and where the best resources are for learning. Then we'll start talking about some of the most fundamental high-level concepts of working with blockchains, such as what is a blockchain, what is consensus, what are blockchain oracles, and what are hybrid smart contracts. And then we'll make our first transaction. If you've never owned an Ethereum wallet or blockchain wallet, we'll get you set up with one of those. We'll use some tools to learn how to see what transactions look like. We'll learn a little bit about gas fees and different blockchains and how different blockchains work. And then we'll learn some of the real core cryptography behind what's known as public and private keys. And then finally, we'll talk a little bit about the future and what's happening in the world today, such as layer 2s and DAOs and different protocols. So with that, have fun and enjoy. Hello everybody, and welcome to the freeCodeCamp Blockchain and Solidity Beginner to Expert Full Course Python Edition. We're going to go through everything you need to know for developing on a blockchain using Solidity and engaging in the future of finance. We're going to cover topics that will teach you all the skills you need to become a smart contract expert that you can take with you no matter which blockchain you're developing on. Blockchain engineers are in extreme demand, and they're building billion-dollar applications almost every day at this point. At the time of filming, protocols like Aave, Yearn.finance, and Synthetics have billions of dollars of locked value in them, allowing people to engage in decentralized finance, or DeFi. This allows people to make censorship-resistant moves and so much more. Some of these protocols with billions of dollars are even less than a year old. So whether or not you're brand new to this space or you've been in here a while, hi, my name is Patrick Collins and I live in the smart contract world. I'll be taking you through your journey to becoming a blockchain and smart contract expert. A little bit of background on myself. I'm an engineer and developer advocate on the Chainlink protocol. And I also have my own blockchain infrastructure company called AlphaChain, where I run different nodes and different infrastructure for blockchains, including one of the main technologies we're going to be talking about today, which is Ethereum. I love being a pioneer in the smart contract ecosystem, and I love taking new users like yourself along to the journey with us. And we are going to teach you to become a smart contract expert. Building blockchain and Solidity applications is building a world of more trust and accountability. It means building a financially free future, and we get to be the ones that will go down in the history books as the pioneers of this space. Additionally, blockchain and smart contract engineering skills are some of the most sought after in the world, with an average salary of a Solidity developer being between $150,000 and $175,000. In this video, we're going to teach you how to become one of these developers and go out into the world and participate in the world of smart contracts and the world of blockchain. This course is ideally for engineers who know a little bit of Python programming, and you can have any level of smart contract engineering. Whether you're a complete beginner to blockchains and you don't even know what one is, or you're an advanced Solidity engineer and you're looking to learn more, this is the perfect place for you. Having a little bit of experience in other object-oriented programming language like JavaScript as well will be helpful here too. And if you're brand new to coding in general, that's all right, because we're going to take you step by step through everything. If you do want a little bit more in-depth Python coding video, there is a fantastic freeCodeCamp video in the description. If you do prefer JavaScript, we will also be releasing a JavaScript edition of this video as well. But everything that you learn here will be applicable there, and if you watch both, you'll learn even more. You can find the entire itinerary for this entire course, along with all of the code associated with everything that we do, and additionally discussions and support and everything else in this smart contract kit / full blockchain Solidity course Pi GitHub repository. It has a table of contents and then the entire itinerary of everything that we're going to go over in this course. And like I said, with helpful tips, resources for getting support, and resources for getting help. Now, for your convenience, every single piece of code that we're going to go over in this video has a GitHub repository associated with it. So be sure to grab the link in the description, grab that GitHub repository, and look through all the different repos that we're going to give you. If you ever get lost or need to refer to some code or want to copy paste some code, all of it will be there for you. It'll also be a great place to reference in the future when you're working on some project and you want to remember how to do something. So be sure to start
and refer back to it as you watch this video. So let's talk a little bit about some best practices for watching this video. This space moves really quickly. So if we show you some documentation, it might be a good idea for you to open that documentation up as well, read through it as we do, so you can stay up to speed. Now, we've packed a ton of information into this video, and studies have shown if you try to digest a massive amount of information in a short period of time, your retention isn't as good. So it's highly recommended that every 25 minutes to half an hour, you take a 5-minute break, and then every 2 hours, maybe you take an additional 30-minute or an hour-long break. You can pause, bookmark areas, and come back later and learn at your own speed. There are timestamps in the description that will help you come back to where you left off. And you don't even have to go in order. If you want to bounce around from topic to topic, you're absolutely free to do so. We're also going to get really technical with the fundamentals of blockchain, and if you want to just jump right into Solidity, you can jump down to the timestamps below and get right into it. And if you're watching this on YouTube, you can adjust the speed that I talk and that I give this presentation. So if I'm talking way too quickly for you, you can slow it down. Or if I'm talking too slowly for you, you can have me speed up. So be sure to set me at the pace that you like best. You are highly encouraged to pause, come back, and ask questions. The blockchain and smart contract world is a very collaborative community. So if you have questions, some of the best places that you can go, going to Stack Overflow and tagging your question with the specific technologies that you're working on, make an issue on the GitHub repo that we're working with, go to Stack Exchange ETH and make a question there as well, jump into the Discord of the technology that you're working with, or even on GitHub discussions if those are there. Learning to become a blockchain and Solidity engineer is actually a lot more than just learning Solidity. Becoming comfortable with all the tools in the space is going to be just as essential as becoming familiar with Solidity itself. And continuing the conversation on maybe Twitter or Reddit or any of these other channels, and maybe even showing your stuff in the next Ethereum or Chainlink hackathon are going to be majorly beneficial to increasing your skill as an engineer. Now, before we get actually coding, a lot of people want to understand what is actually happening with all this blockchain stuff. What is blockchain? What is a smart contract? How did this all get started? And understanding these core fundamentals will actually shape the way you code and architect your smart contract applications. So learning these is really, really critical. However, if you're already familiar with blockchain and you just want to jump into the Solidity, feel free to grab a timestamp from the description and jump to that section. Now, since you're here though, you've probably heard of Bitcoin before. Bitcoin was one of the first protocols to use this revolutionary technology called blockchain. The Bitcoin white paper was released by the pseudo-anonymous Satoshi Nakamoto, and it outlined how Bitcoin could be used to make peer-to-peer transactions in a decentralized network. This network is powered by cryptography and allows people to engage in censorship-resistant finance in a decentralized manner. Due to some of the features of Bitcoin, a lot of people took it to be as a superior store of value over another asset like, let's say, gold. And that's why it's commonly referred to as digital gold. Similar to gold, there is a scarce and set amount of it on the planet, and people use it to buy and sell, similar to other assets. You can read more about the original vision in the white paper, and there's a link to it in the description. Now, this was a fantastic breakthrough, and in a little bit, we're actually going to look through how blockchains can actually work and how all of this is possible. But some people took this and saw this technology and thought that they could do even more. A few years later, a man named Vitalik Buterin released a white paper describing a new protocol called Ethereum, which used this same blockchain infrastructure, but with an additional feature. And in 2015, they released this project called Ethereum. Him and a number of other co-founders took this blockchain technology and applied it in ways that people can make entire decentralized applications, decentralized organizations, and build smart contracts and engage in agreements without a third-party intermediary or centralized governing force. Their idea was to take the same pieces that made Bitcoin great and add smart contracts to it. And in fact, this technically wasn't even a new idea. Back in 1994, a man named Nick Szabo proposed a technology called smart contracts. A smart contract is a self-executing set of instructions that is executed without a third-party intermediary. They come to life on a blockchain. And these smart contracts are really going to be the core thing that we're going to be working with and we're going to be developing. Smart contracts are similar to regular traditional contracts that people make between each other. But instead of writing these contracts down on pen and paper or typing them on the computer, it's entirely written in code. The terms of the agreement are written in code and automatically executed by the decentralized blockchain network instead of being written in pen and paper and executed by the 2 parties or 3 parties or however many parties involved. This was one of the main differentiators between the Ethereum protocol and the Bitcoin protocol. Now, technically, Bitcoin does also have smart contracts. However, they're not Turing complete, meaning that they don't have the full range of capabilities as a Turing complete application like Ethereum. This was actually an intentional move by the Bitcoin developers. They view the Bitcoin network as an asset, whereas Ethereum and the Ethereum developers viewed that asset as an asset and also a utility for people to build these smart contracts.
Now, these smart contracts are revolutionary technologies, and we're going to talk a little bit more about what their advantages in a little bit. But they actually come with a fatal flaw with what's known as the oracle problem. These blockchains are deterministic systems, and we'll learn why they're deterministic very soon. And this determinism means that they're a walled garden, meaning that everything that happens in these smart contracts and on this blockchain happens in this little box. Now, of course, if we want these smart contracts to actually be these digital superior agreements, then they need some way to interact with the real world and get real data and external outside the blockchain computation. This is where oracles come into play. Oracles are devices that bring data into a blockchain or execute some type of external computation. So great, so oracles are the solution. Now blockchains can talk to the real world, right? Well, not quite. Our blockchains and smart contracts are these decentralized applications. And in order for them to stay decentralized, that means they would also need to get their data and external computation from a decentralized manner as well. Your on-chain logic will be decentralized on the blockchain, but you'll also need your off-chain data and external computation decentralized as well. Combining these on-chain logic settlement layers and these off-chain data and external computation builds what's called hybrid smart contracts. And a large majority of DeFi applications and the largest applications today are these hybrid smart contracts. This is where the protocol Chainlink comes into play. Chainlink is a decentralized modular oracle network that allows you to bring data into your smart contracts and do external computation. And it's these hybrid smart contracts that can have this on-chain settlement and interact with the real world in some meaningful way. Chainlink is an incredibly powerful oracle network because it allows us to get data, get randomness, do some type of upkeep, or really customize our smart contracts in any way we want and elevate them to do anything that we want them to do. Now, throughout the course, when we're talking about smart contracts, oftentimes we are also talking about hybrid smart contracts. Smart contracts is used a little bit interchangeably with hybrid smart contracts, but just know that when we say hybrid smart contract, we're talking specifically about smart contracts with an off-chain component. Now, throughout this video, you'll hear people say smart contract, you'll hear people say decentralized protocol, decentralized application, or dApp, and they kind of all are a little bit interchangeable. A decentralized application is usually a combination of several smart contracts, and when we start coding some Solidity, you'll see what a singular smart contract or singular contract looks like. Smart contracts are going to be what we code, write, and deploy for the majority of this video. And learning some of these fundamental concepts will allow us to be better smart contract and better Solidity developers. Now, since its inception, the Ethereum protocol has given rise to many new paradigms and industries, including DeFi, NFTs, DAOs, or decentralized autonomous organizations, layer 2s, and so much more. And a couple of other protocols have taken this Ethereum vision and gone in a different direction with it, like Polygon, Polkadot, or Avalanche. If we learn the core basics of smart contract development on the Ethereum platform, all of these skills translate to these other chains as well. So don't worry about learning a specific tool or chain because most of them work together pretty seamlessly. Now, there are a few exceptions to this rule, and there are some smart contract platforms, aka blockchains, that don't use Solidity. However, learning the fundamental skills here will still translate to every single other blockchain. And Ethereum is by far the most popular and most used smart contract blockchain or smart contract protocol. You'll also hear those words used a little interchangeably as well. Sometimes I'll say blockchain, or sometimes I'll say smart contract platform, smart contract protocol, and the like. Similarly, Chainlink is the most popular and powerful decentralized oracle network, and is going to be the one that we're going to focus on here.
Chainlink is also blockchain and smart contract platform agnostic, meaning it'll work on Ethereum, Avalanche, Polygon, Polkadot, or really any blockchain or smart contract platform out there. Whew. Even in this introduction, we've already learned a lot. So let's do a quick summary of what we've talked about. Bitcoin was the first application to take the blockchain technology into the limelight and into a meaningful way. Bitcoin is a sort of digital gold, able to make transactions between users as almost a sort of currency. Ethereum takes this blockchain technology one step further, but you can also build smart contract or decentralized applications, decentralized autonomous organizations, and more, because you can code with smart contracts. These smart contracts can then access external data and external computation outside the blockchain using what's called oracles. Chainlink is the most powerful decentralized oracle network and allows us to build these hybrid smart contracts, which is a combination of decentralized on-chain logic settlement layer and any decentralized external off-chain data or computation. Hybrid smart contracts and smart contracts are often used interchangeably. Now you're probably asking yourself a lot of questions right now, like what makes Bitcoin so interesting? What makes it like a digital gold? And how are these smart contracts going to add any value to the real world? And that's what we're going to go into now. So before we get into the nitty-gritty of how these blockchains and how these smart contracts actually work from a low level, let's go high level and talk about some of the features and massive advantages that blockchains and smart contracts have over our traditional environments. The first feature that these have is they are decentralized, and you'll hear this term used a lot because it has a massive benefit. Blockchains are decentralized, meaning there's no centralized source that controls the blockchain. The individuals that make up blockchain are known as node operators, and they are the independent individuals running the software that connects the whole blockchain together. It's all these different independent individuals that make the blockchain and blockchain-like networks decentralized. We'll dive deeper into that concept later. A great example of why this is so fundamentally groundbreaking is if we go back to what happened recently, even with Robinhood and GameStop. GameStop shares were no longer allowed to be bought because a centralized entity didn't want them to be bought anymore. So they flipped a switch and nobody could buy that stock anymore, essentially having a single entity controlling the entire financial market. The fact that a single entity has the power to make these choices for us is a travesty, and blockchain is here to solve that. There's a narrative here called the bankless narrative, where users can actually live in a world where they don't have a bank. Banks, while good in their own right, have a history of doing some shady things. They also have the power to potentially freeze your funds, not letting you withdraw or move or do anything, because they are a centralized entity that again can flip a switch and control how you interact with your life every day. Being free of these centralized entities have this much power and this much control over your life has widespread positive ramifications. Transparency and flexibility. Everything that's done on a blockchain and all the rules that are made can be seen by everyone. There's no backdoor deals, there's no shady happenings. Everything that happens on chain, you can see. This means that there's no special information that a few have. Everyone has to play by the same rules, and everyone can see exactly what those rules are. Now, additionally, this doesn't mean that everything you do is tracked. The blockchain is pseudo-anonymous, so you can create different accounts and you can interact with it in many different ways. This leads me to my freedom point, but I'll get there in a second. Speed and efficiency. Have you ever tried to make a withdrawal from the bank and it took 3 to 5 days? All the bank is doing is adding and subtracting numbers. Basic first grade math. So why does it take so long? Because blockchains are verified by a decentralized collective, the settlement or withdrawal period in this case is substantially faster. And depending on the blockchain that you're using, it can be from 10 minutes all the way down to just a couple of seconds. In the stock trading or hedge fund world, it can actually take up to a week for your buy or sell of a stock to go through. Security and immutability. Blockchains are immutable, which means they can't be changed. And because of this, it means that they can't be tampered with or corrupted in any way, shape, or form. This allows us to have massive security on our data, on our transactions, and anything of the like. If your computer goes down and your backup computers go down, in the regular world, your data is gone. If all your data is on those two computers, you're out of luck. On a blockchain, if several nodes go down, it doesn't matter. Because as long as one node in the entire system is running, the data is safe and secure. There are thousands or hundreds of thousands of nodes running these blockchain softwares, meaning that everything that happens and is immutable and won't change. Hacking the blockchain is nearly impossible and substantially harder than hacking a centralized entity. And this is also much more secure in the asset sense as well. Instead of having gold in a vault or a contract written on a piece of paper or on your computer, you have an asset that is locked on the blockchain forever. And all you need to do to access it is have a private key or mnemonic, which is essentially a password. So you don't have to lug your gold around or lug your contracts around with you. It is always on the blockchain. Smart contracts in particular remove a massive conflict of interest. In the traditional world, when we engage with users or individuals, they don't always have our best interests at heart. A lot of them are usually self-motivated in some sense. And there's nothing wrong with that. That's how a lot of people are. However, when we make an agreement with them, this agreement can have a massive conflict of interest with the user who's supposed to execute that agreement. Let's take insurance, for example. If I pay an insurance provider $100 a month, I'm paying them $100, and in the event that I get hit by a bus, we've made an agreement or a contract that they're going to pay my medical bills or bail me out. However, they have this massive conflict of interest. Insurance companies aren't in the business of giving out money. They're in the business of making money. So even though they've signed this agreement, when this event occurs, they still don't want to pay this money out to me. And if they can find a loophole in the contract, they will, because that is what they are motivated to do. So they sign this agreement, but it's not in their best interest to do so. So they have this massive conflict of interest, and this is native in all of the agreements that we make today. They are the ones who decides whether or not they're going to execute their agreement. Giving execution power to the party that doesn't want to execute something has often led to frustration. Now, the follow-up is you can always sue them and go through these processes, but now you're wasting all this time going through this long process to get something that you should have originally gotten in the first place. This leads me to one of the biggest value adds of smart contracts. Smart contracts allow us to engage in trustless and trust-minimized agreements. We currently live in a world of brand-based agreements. If I engage in some agreement and I don't like the service that I'm provided, my alternative to this is to waltz down the street to another brand, to another service who's going to make the exact same set of promises to me. And then I have to trust them that they're going to execute faithfully. Smart contracts allow us to move from this brand-based agreements to math-based agreements. These math-based agreements, we don't even have to trust that they're going to do the right thing, hence the name trustless. 1 + 1 is always going to equal 2 in a math world. Whatever the code determines is the input-output, that's exactly what's going to happen every single time. Now for me, these really all add up to 2 major pieces: freedom and trustless. All these pieces allow us to live in a world that's more accountable, more trusting, more friendly, and just better. It allows us to work in an environment, in a universe where things just work. It allows us to do the freedom to engage with other people how we wish, because there's no centralized controlling body influencing every action that we make. All the rules are the same and nobody's getting special treatment. This brings out this new world of economic opportunity as well. And as our lives become more and more digital, we're constantly being bombarded with centralized services that want us to use their interface so they can profit on how we interact and force us or push us to making the decisions that they're motivated for us to make. Smart contracts, decentralized applications, and blockchain allows us to be free of these repressors and live in an environment that's truly free and trustless. So with all that high level being said, let's do a quick summary of what we just learned. Blockchains are decentralized, meaning that they are not controlled by a single centralized entity. It is run by a network of independent users. Transparency. Blockchains are transparent. Everything that happens on a blockchain, everybody else can see and everybody else can work with and see that everyone's playing by the same rules. Blockchains are quick and efficient, especially when it comes to monetary policy. Settlement on blockchains are fast and easy. Immutability and security. Blockchains can't be changed or tampered with or corrupted and are incredibly, incredibly secure. Smart contracts remove the massive conflict of interest traditional agreements have. Smart contracts allow us to move away from political brand-based agreements to secure math-based agreements. Smart contracts allow us to engage in trustless and trust-minimized agreements. Smart contracts are a set of instructions which, when placed on a blockchain, are self-executing pieces of code not run by any centralized intermediary. In addition, smart contracts are typically paired with some type of oracle to get some information about the real world. When smart contracts are paired with an oracle, they're called hybrid smart contracts. Chainlink is a secure, decentralized, modular oracle network used to bring data into your smart contracts and also make some type of external computation. I also briefly want to mention DAOs, or decentralized autonomous organizations. You'll hear this referred to a lot as well. Decentralized autonomous organizations are organizations that live online and live in these smart contracts. They're similar to a regular organization in the traditional world. However, they have people who maybe hold governance tokens to make voting decisions, or they do all their governance on chain, on this decentralized settlement layer, giving us the freedom to engage with each other as we please. So now that we've taken our first dive into blockchains and smart contracts, and at least from a high level understood why they're so advantageous, let's jump in, let's get an Ethereum wallet, and let's make our first transaction on a live blockchain. Are you ready?
Now let's jump into Ethereum. We're going to make our first interaction with the Ethereum blockchain. And once we do this interaction, once we make this transaction, then we're going to go back and look at what actually happened. What were the technical implications that allowed this transaction to go through? So in order for us to interact with the blockchain, the first thing that we're going to need is an Ethereum wallet. So I'm going to go ahead and go to MetaMask because it's one of the most popular wallets and one of the easiest to use. We're going to go ahead and download it. I'm using the Brave browser, but it works for Chrome, Firefox, or really any other browsers. And it's just going to be a little extension in the top right hand of your browser. This way we can really easily see at any time what we have in our wallet. This will store all of our Ethereum based currencies. So I'm going to go ahead and install MetaMask for Brave, add to Brave, add extension. And now we can go ahead and get started with working with Brave. This is the first step you absolutely need to take when starting your journey, and one of the easiest steps to take. So we're going to go ahead and get started. And we're going to create a brand new wallet. So we're going to go ahead and hit create wallet. If you already have a wallet, you can actually import it via I have a seed phrase. And we'll talk about this seed phrase or secret phrase in a little bit. So let's go ahead and create a new wallet. And sure, we'll agree to help out MetaMask. Now we will create our password. Make sure that this is really secure. For the purpose of this demo, my passwords are just going to be password, but please don't have that be your password. Now, when I'm doing my testing and when I'm doing my coding, I actually use a separate account from the account that I actually have real money in. However, if you want to use this account and actually put real Ethereum and put real money into it, you absolutely 100% need to back this up. So we're going to go ahead and click reveal secret words. I'm showing you guys here because this is just a demo and I don't really care. However, if you show this secret phrase to anybody else, they will have access to all the funds in your wallet. So everything that we're going to do in this tutorial, we're going to use fake money. We're going to use not real money, so it doesn't matter. However, if you're going to actually put money in here, you absolutely need to have this written down, because if you lose access to this and or your private keys, which we'll talk about in a little bit, you will lose access to your wallet and you will lose access to all your funds. So they give some tips like store this phrase in a password manager like 1Password, write this phrase down on a piece of paper, put it in a secure location, memorize it. Whatever you want to do, just make sure you have this backed up somewhere. I'm just going to go ahead and hit download this for now, and I'm going to save it on my computer. It's not best practice to save it to your computer. It is much better to use a password manager or write it down on a piece of paper or something. But again, because we're just demoing here, I'm going to show you it here, and we're not going to put any real funds into this. So we're going to go ahead and hit next, and it's going to ask us to make sure and it's going to ask us to verify that we actually have it written down. And we're going to go ahead and hit confirm. And great, and it gives us a couple other tips. Remember, definitely take these tips very seriously, especially if you're going to use this for real money. Like I said, for this demo, we're just going to use test money, so it's not as big of a deal, but if you put real money in, you absolutely need to back up this seed phrase or secret phrase, or we're going to refer to it as our mnemonic phrase. Awesome, now we can see the user interface of this wallet. And depending on your browser, if you actually go ahead and look in your extensions, you can pin it to your browser, and you can even just click it and get the same interface here. Let's take some inventory of what is actually going on in here and what we actually have. Our mnemonic phrase, that secret phrase that we got, has given us access to a new account. And here's the address of our account. We can use a tool like Etherscan to view different addresses and what's been going on with them. So if we look at this address that we just created on Etherscan, we can see that no transactions have happened. It's empty. It has 0 Ether in it. It has $0 worth of value in it. And this address here is our unique address. This address represents exclusively this single account that we just created. We'll talk a little bit more about Etherscan in a bit, as it's a tool that we're going to use more and more. Now we can even click this circle here, and we can even create more accounts and give it a different account name. We'll call it account 2. This one has a different address. So if we go ahead, go back to Etherscan and look this up, this one has a different address here. So we can have multiple addresses in here. And now if I click this, I have 2 accounts, account 1 and account 2. The mnemonic that we've been given gives us access to create multiple accounts with that same mnemonic. So having that mnemonic will give us access to every single account that's ever created with that mnemonic. This is why securing your mnemonic is so crucial, especially if you create multiple different accounts. Now each account has a unique identifier with them as well. So this right here is the public address. When we copy this, this is the public address of that account. However, there's also a private key to work with this account, a secret key. And we can go ahead and view it by clicking these 3 dots, go to account details and export private key. Put our password in and confirm. So this is going to be our private key. So this is a single password associated with this account. If you give somebody else access to this private key, they will have access to my account 2. They won't have access to my account 1 because the private key of account 2 is only associated with account 2. The mnemonic, however, is associated with all accounts. And this is why when people say store your private keys in a safe place or store your keys in a safe place, they're usually referring to both your mnemonic and your private keys. If you lose your private key, you lose access to this account. If you lose your mnemonic, you lose access to all your accounts. So long story short, back up your mnemonic since it has access to everything, and back up your private keys too, but just keep in mind they only have access to the individual accounts. And great, those are some of the main security pieces here. Now, what else is going on in MetaMask is we can see this section here that says Ethereum mainnet. If we click it, we actually see a bunch of other networks in here. So when you buy ETH and when you work with ETH, you're working on the Ethereum mainnet. When you interact with smart contracts or DeFi or any things that we're going to talk about later on mainnet with real value, you're going to be working on the mainnet. However, since we're engineers, oftentimes we're going to want to test our applications or do some type of integration tests or just make sure our code actually works. So there's also what's called testnets. These are networks that resemble Ethereum and work exactly the same way as Ethereum does. However, they're not with real money and it's just for testing your applications. So we can even go to Etherscan and look up Rinkeby Etherscan. We can see the Rinkeby test on Explorer. We look up at our address and it's the exact same information here. Nothing has gone on Rinkeby. And this is totally different. So when we make a transaction, these are all different networks. And if it says test network, it's made to be made without real money. Later on, we're actually going to show you how to work with other EVM compatible chains. Don't worry about what EVM compatible means for now, but we can work with Avalanche, Polygon, and other applications through this networks interface as well. So remember, a testnet blockchain is a blockchain where the currency doesn't have any real value, but it resembles and acts exactly like the Ethereum mainnet so we can test our applications. so we can test and practice our applications. In fact, what we're going to do right now is make our first transaction on the RinkB testnet.
And this will simulate exactly what it's like to receive a transaction on the Ethereum mainnet.
So we're going to go to this application called the RinkB faucet. This is where we're going to make our first transaction.
You can additionally find this link in the GitHub repo associated with this course. And then we're going to come down here and we're just going to switch to RinkB, or you could just put this right into your browser.
RinkB is going to be one of two testnets that we're actually going to work with. The other testnet that we're going to work with is going to be Kovan. It's important to know how to switch between testnets and EVM compatible chains, which is why we're going to be working with both. For now, we're just going to be working with RinkB. A faucet is a testnet application that gives us free test Ethereum. Hence why it has no value, because anybody can get it for free from one of these faucets.
So to get some testnet Ethereum from this faucet, all we have to do is scroll down. I'm not a robot. We'll complete the CAPTCHA. Go ahead and verify. You're going to come to your MetaMask and just copy your address. It doesn't matter what network that you're on. The addresses are always going to be the same, but we are going to be getting Ethereum to our address here. Copy the address. We'll come back here. We can uncheck 10 test link for now. We'll paste the address in here and then just hit send request. And we'll get a little screen like this that pops up. After a little delay, we'll get this transaction hash here for our transaction. If you want more ETH here, you can just close and re-request, wait the delay again, and you will receive the additional ETH. If we scroll up into our MetaMasks, we can indeed see we have the 0.1 ETH right now in our RinkB testnet. Obviously, for the other testnets, we will not. But we can see the 0.2 ETH now that this has completed. And additionally, if you want to get something from Kovan, you do the same thing. Post your address in here, uncheck the request type, send request, and after a brief delay, if we look in our MetaMasks, we can go to Kovan, and we'll indeed see the ETH in our MetaMask here. So when we first made this tutorial, there was a faucet that gave out 18.75 ETH. Now we're using this one instead. So what we're going to do then is we're going to continue with that video, the 18.75, on the RinkB chain, but for you it'll be this lower amount, obviously. So we'll want to copy the address here and go to RinkB Etherscan.
We go over to RinkB Etherscan. We now see that the balance is 18.75. And we can even see that in our wallet. On the RinkB network, we have 18.75 ETH. But again, if we look at mainnet, we have nothing there. If we look at Ropson, we have nothing there. If we look at RinkB, we have 18.75, right? So these are very different networks. And we've just made our first transaction. We've been given 18.75 ETH. And if we refresh this page, we also see that this is our first transaction that was made. Some account sent us 18.75 Ether from this account to us. And we can actually even look at the details of this transaction. Etherscan is what's known as a block explorer. Block explorers are applications that allow us to see details of things that happen on a blockchain easily. We can see the transaction details of this transaction here. And whenever we work with smart contracts, we will also see them in a transaction similar to what we're seeing right here. And again, we'll talk about that soon. Now we can see a number of information here. We see a unique transaction hash. This hash, or this unique identifier, uniquely identifies this transaction as the key of what this transaction is. We see that it was a successful transaction. This is the block number, which we'll talk about in a little bit. We see it was from this unique account, which looks like they did a ton of transactions because this is the faucet account, to our account that we created. Value was 18.75 Ether. And then we have these transaction fees, gas price, gas limit, and gas used. Now, gas refers to the fee paid to node operators for successfully including a transaction in a blockchain. Now, exactly how this works is actually going to change pretty soon, but the concept is basically anytime you want to change the state of blockchain, whether this is sending some Ethereum, or making any type of transaction, you actually have to pay a little bit of Ethereum or a little bit of that native blockchain token to actually execute that transaction. Whenever we do something on the blockchain, it costs gas. And if we do something that would take a lot of energy for the blockchain to do, it will cost more gas. So if I send a single transaction, that's going to cost 21,000 gas. However, if I were to send a transaction that called a smart contract function and did a whole bunch of other stuff, it would cost more gas. So we see here, when we got sent 18.75 ETH, whoever sent us that ETH also paid the blockchain miners or the blockchain validators a little bit of Ethereum to include our transaction. Now, we actually get to pick how much of a fee we want to send with our transactions. So let's look at another example. So in our accounts in MetaMask, let's even expand the view here. We have two different accounts. We have account 1 and account 2. Account 1 has 18.75. Account 2 has 0. We can actually send money from account 1 to account 2. And again, remember, this is all fake money. So we're going to go ahead and hit transfer between my accounts. So we're going to send money to account 2.
Hi all, this is actually Patrick from the future. Quick update here. So MetaMask recently updated what their user interface looks like due to a new proposal in Ethereum. Gas has actually changed a little bit. Now, I'm not actually going to go into the specifics of how it's different because essentially it's pretty much the same with a couple of nuances. But I do just want to say that the user interface is going to look a little bit different. So if I look to send some ETH, when I hit next and I want to see gas fees, I'll hit edit here and I can choose advanced options. And this is where I can choose the advanced gas fees. If you don't want those advanced options, you can just use medium, high, or low. In the video that we're going to show, it's a little bit older version of MetaMask, but essentially this is what I'm referring to in the video when I'm talking about these gas fees. It's going to be these metrics here.
And here's where we can see some transaction details. And we see the asset that we're going to send, which we only have Ethereum in this wallet. So we're only going to send Ethereum. Later on, we'll learn how to get different assets into this wallet. We're going to choose an amount. I'm just going to choose to send 1. And then we have these pieces here associated with the transaction fee. So we have a gas price in Gwei and a gas limit. So when we send a transaction, we can choose a gas limit. We can say, hey, if this transaction is going to spend more gas than 21,000 gas, we're not going to do it. We also get to set a gas price in Gwei. But here's the quick example of Gwei versus Ethereum. 1 Ether is this many Gwei. And 1 Gwei is this much Ether. Because if we just said, hey, could you send me 0.0000001 Ether, that would be kind of really obnoxious. So we just say, send me 1 Wei or send me 1 Gwei. So I know we've been throwing this gas term around for a little bit, but here is it basically simplified. Gas is going to be the measurement of how much computation something uses. The gas price is going to be how much it costs per unit of gas. A gas limit is going to be the maximum amount of gas that can be used in a transaction. So for example, if we make a transaction that uses 21,000 gas and each 1 gas is 1 Gwei in price, that means we're going to pay 21,000 Gwei in transaction fee. So back in our transaction, we're saying the gas price is going to be 1 Gwei. So the transaction fee is going to be the gas that we use, which will be up to this gas amount, times the gas price. So it'll be 21,000 Gwei will be the transaction fee. So then the question is, well, why would we ever bump it up? Why would we want to pay more gas price? Why do I even have the option to pay more? Well, and this comes down to block space. We'll talk about this a little bit more when we get into how the blockchain actually works, but the blockchain can only process so many transactions at a time, and nodes and blockchain nodes can only process so many at a time. So when I make a transaction, a node has to decide why they want to include my transaction into the block. And if there are a ton of people looking to make these transactions, then the nodes are going to be highly incentivized to pick the transactions that are going to give them a high price, that are going to give them a lot of money for including that transaction. So this is what's called ETH gas station, and it is a gas estimator of the blockchain. it currently says that if you want to get your transaction in right away, it's going to cost you 31 gwei to do so. If you want to get it in less than 5 minutes, it's going to take you maybe about 21 gwei. So the gas prices of Ethereum fluctuate with how much people use it. And the gas prices of all these blockchains fluctuate with how much people use it. So this is an important concept. So typically, when you're setting your gas price in a transaction, you can take a look-see at each gas station and say, okay, if I want mine to go in right away, I'm going to do ASAP. If I want to go in fast, maybe I'll do this fast amount. Standard, I'll do this standard amount. But it all depends on how many people are looking to work with this blockchain at the same time. And as you can see, it fluctuates pretty quickly, right? It just went all the way up to 46. So maybe more people are using the blockchain. Now, this is obviously for the ETH mainnet, and on the testnet, there's not going to be that same competition, but we can still change it anyway. So if I go ahead and do 100 for the gas price, and I hit next, and I hit confirm, if I go to activity, I now have this transaction in my MetaMask. But I can go ahead and view this on Etherscan as well. And we can see this is what it looks like when it's still processing this transaction. And now I can see that it's passed. And now if we look at the gas price, we see it's 100 gwei. And this is what we set it as when we were working with it before. So gas price is 100 gwei here versus our first original transaction was just 1 gwei. And now if we look at our MetaMask, we can see that the funds have indeed been subtracted from this account and they have been added to this account. Now there's 1 ETH in this account. Awesome. And you can see the activity. There's 1 ETH in here. So again, the reason that these gas prices exist is because nodes can only put so many transactions into a block. So they're highly incentivized to input the transactions that are going to give them a higher fee. So in times when a lot of people are looking to use a blockchain, prices will get very high. And when very few people are using a blockchain, prices will be very low. This Etherscan tool is incredibly, incredibly powerful, and we'll be using it more and more as time goes on. Now, here's something that's incredibly exciting. With just this little bit of information, you now know how to interact with blockchains and interact with the Ethereum protocol. So if you don't want to learn how to code anything, you can go and you can start interacting with Ethereum and interacting with protocols with just this much information. However, I know most of you guys are here to learn how to code. So let's look under the hood of Ethereum and what is actually going on with these transactions and with these gas and with these blockchains and what's really going on. Let's learn all the fundamentals of a blockchain. Now, if you want to just go ahead and jump into the coding, go ahead and grab a timestamp from the description. However, learning exactly how the blockchain works is going to make you an incredibly powerful developer. So let's take a look at that first. So we're going to be going through this blockchain demo on this site right here. Now, the creator of the site has a fantastic video and a fantastic walkthrough, Blockchain 101. It is right on their site. So if you're looking for another explanation, definitely check out his video. It is absolutely fantastic. But the first thing that we really need to do in order to understand blockchain, in order to understand really anything and everything that's going on here, we first really need to understand this SHA-256 hash, or hashing just kind of in general. Let's first understand what a hash is. A hash is a unique fixed length string meant to identify any piece of data. They are created by putting some piece of data into a hash function. In this example, the hashing algorithm used is SHA-256. Now, Ethereum actually uses this right here for its hashing algorithm, which isn't quite SHA-256, but is in kind of this SHA family. But it's really just another way to hash things, and the specific hash algorithm doesn't matter so much. So this example uses SHA-256, but you can imagine it's the same as the Ethereum hash. They're just going to result in a different hash. So what's going to happen in this application here is whatever data or whatever information we put into this data section here, as you can see below, this hash changes. So what's happening is this data is running through the SHA-256 hash algorithm, and it's outputting this unique hash. So this hash is a unique fixed length string that's going to identify like a blank data piece here, right? So if I put in, my name, like, Patrick Collins, this is the hash that's going to represent Patrick Collins, right? And you can see, even when I put, tons and tons of data in here, the length of the string doesn't change, right? So it's always going to be the same amount. We can put almost any amount of data in here. There is an upper limit on the max size of the data, but for all intents and purposes, we can pretty much put any length in here. And you'll see too that, every time I type in Patrick Collins, this hash is always going to be this 7E5B, right? I'm going to delete it. I'm going to do Patrick Collins again. 7E5B. It's always this unique hash is always going to be unique, right? It's always going to be this fixed length string here. So now we can take this idea, right, of putting this data in here, and we can move on to this concept of a block. So with this block concept, we're going to take the exact same thing with this hash, this data section, right? But instead of having everything just being in this singular data area right here, we're going to split this data up into block, nonce, and data. So what we're going to do is we're actually going to hash all three of these to get this hash, right? We're going to put all three of these. We're going to say all three of these are combined together. We're going to put all three of them into this hashing algorithm to figure it out. So if I type a bunch of stuff here, we can see that block 1 with nonce, this nonce and this data, we're going to get this hash. And as you can see, actually, the screen turns red. This block turned red. Now, what happens when I hit this mine button? When I hit this mine button, it's actually going to take some time. It's going to think for a little bit. And we can see that the nonce here actually changed, right? The nonce is different from what it was before. And this hash now starts with 4 zeros. Okay, and then the back turned green. When we're talking about mining, we're talking about miners solving some type of very difficult problem that takes a lot of time to do. Now, in this example here, the problem that the miners had to solve was they had to find a nonce or a value in this nonce section that when hashed with at block number 1 with this data, it would start with 4 zeros. So the problem here the miners had to solve was to start with 4 zeros. And the only way for them to really do that is kind of this brute force, trying stuff. So they tried 1, okay, 1 didn't work. Okay, 2, nope, 2 didn't work. 3, no, 4, 5, 6, okay, 5, well, that started with 1 0, but that's not 4. And they have to keep trying all these numbers until they get to this one where, let's hit mine again, where it has 4 zeros at the start. Now, this specific problem changes blockchain to blockchain, right? Ethereum has a different problem for miners to solve. Bitcoin has different problems for miners to solve, but this concept is going to be the same. So they have to take one block is going to be this concept is going to be all this data. It's going to be the block number, and it's going to be this nonce, right? And so this nonce is the solution. Is going to be the number that they use to get like the solution to the problem, right? So if I go to 1. Here, and I do this again, we're going to hit mine, and the nonce has changed, right? It went from 1 to 33,128 because this is the nonce that allowed this hash to start with 4 zeros. And so that's what's happening when blockchain miners are mining. They're going through this process, this very computationally intensive process of trying to find a nonce that fulfills whatever the problem is. So that's really it, actually. So that's a block, and that's really what's happening when miners are mining. They're just looking, there's trial and error, brute force, trying to find this nonce. So now that we know what a block is, let's go to the next step and figure out, okay, well, what's a blockchain? So here we have an example of what a blockchain is going to look like, right? We have a combination, we have back here in the block section, we have what one block looks like. Now here we have multiple different blocks, right? Each one of these represents a different block, but we have an additional column here, or we have additional variable here. So like before, we have block, nonce, and data, right? We have block, nonce, data, but we also have this thing called previous, right? And so this is actually gonna be pointing to the previous hash of the last block. So for example, if we go to the last block in this blockchain, it says previous is 00AE8, and if we look at the hash of block number 4, it's 0000AE8. And then we look at its previous, it's 4 zeros B9, we have 4 zeros B9, and so on, all the way back to our first block, which has previous of just all zeros, right? And so the block with the previous of all zeros is going to be known as the genesis block. So you've probably heard that before, the genesis block. It's the first block in the blockchain where the previous hash points to a hash that doesn't actually exist. Now, as you can imagine, kind of the same as how this block worked, how the block, nonce, and data all go through the hashing algorithm. In the blockchain, the block, nonce, data, and previous hash all go through this hashing algorithm to figure out, what the hash is, okay? So if we go to over here, for example, if I type in, Patrick, obviously this is now no longer valid, right? Because this nonce combined with the block, the data, and the previous hash aren't going to solve, our problem of having 4 zeros at the start, right? So I'm going to go ahead and fix that. And that's kind of an easy way to see it being broken. But let's take a look. If I break this block right here, what happens if I break the data in here? If I do like trick in here, you can see that both of these are now red. Both of these are now invalid, right? Because the block hashed with the nonce, hashed with the new data, which is my name Patrick, hashed with the previous block, is now a brand new hash, right? And this block is still pointing to this previous hash right here, right? Is pointing to this previous block, and now it is wrong and it is messed up, and now its nonce with this previous hash is also wrong, right? And this is where, when we talk about blockchains being immutable, this is exactly how it's immutable, right? Because if I go back and I change anything, if I just typed A right here, the entire blockchain is now invalidated, because none of these are going to have nonces that solve this equation anymore. So this is why blockchains are immutable, is because anytime you change one thing, you ruin the rest of the blockchain, okay? So however though, if an A was here originally, we can go ahead and mine these. We can mine all these, but as you can see, this is going to start getting very computationally expensive, because I have to go redo basically the entire blockchain. And the farther and farther down the line you get, the harder and harder it becomes to rehash and redo all these different blockchains here. Now this makes a lot of sense, right? So we have this blockchain. It's really hard to change something in the past, but if we do, we can just go ahead and remine it. Now, if I'm the one who controls the blockchain, right? If I'm the one who controls this, and I want to change something in the past, well, okay, great. All I got to do is change this data here, and then, mine each one of these. Obviously it's going to be very computationally expensive, but it's something that I can do, right? If I'm the one who owns the blockchain. Now, here's where the decentralized nature or the distributed nature really makes it incredibly powerful. So we're going to go to the distributed tab here, which I also refer to as the decentralized tab here. And it's going to show us what a blockchain looks like in a decentralized manner. So we have this exact same initial setup here. We have distributed blockchain. We have our first blockchain, which is kind of exactly as the one from here. But we also have more than one. So we have peer A, peer B, and peer C. And when people are talking about peer-to-peer transactions, they're really talking, this is kind of that concept that they're talking about, right? So we have a number of different peers who are running this blockchain technology. They're all weighted equally, right? Each one of these peers, or each one of these nodes, each one of these entities running a blockchain has the exact same power as anybody else, right? So the way that we can tell very easily which blockchain is correct or which ones are correct are by looking at this end hash here, right? Or by looking at where we are in the blockchain. Because again, remember, this hash that this in this last block here is going to encompass all of the blocks from before, right? Because this last hash is going to have the previous hash here, which includes the previous hash here, which this hash includes the previous hash here, so this last hash encompasses everything in here, right? And we can look at the hash of peer C, which is 4 zeros and then E4B. We can look at the latest hash of peer B, which is 4 zeros E4B, and then peer A, which is 4 zeros E4B. So all of these peers, all of these nodes, all of these decentralized, these independent, all these independent users running this blockchain software, they're all matched up. It's very easy for their nodes to look at each other and say, hey, great, we are all matched up. Now, let's say that A decides that, something happened on the blockchain that they didn't like and they wanted to go back and change something, right? So let's say they change here, obviously the rest of their blockchain is invalidated and they have to spend a lot of computational power to catch up to speed. So let's go ahead and humor it. Let's say that they did. They ended up catching up. They ended up mining everything. And now they have a valid blockchain, right? It solves the equation. Awesome. However, in block number 3, there's something new, right? This is here and it shouldn't have been here. This is something that peer A put in by themselves. All that happens now is we look at all the blockchains that are running the software and we're looking at all the hashes at block number 5. So peer A has this new hash now, 0009BC, but peer B has a different hash, 000E4B, right? So who's right? Is it peer A with their new stuff or is it peer B? Well, that's where the decentralizer comes in, because then we can look at peer C, and peer C also has E4B. So peer B and peer C both say, hey, peer A, you're wrong, get out, right? And peer A will stop being able to participate in the mining rewards because they have essentially forked the blockchain and started their own little blockchain, right? With their own history, because they're the only ones with this piece of data in block 3, whereas peer B and peer C have nothing in there. So that really shows why in these blockchain worlds, in this decentralized world, there really is no centralized entity. Peer A, might have been maliciously motivated to change, this block number 3. However, democracy rules, right? The majority rules in the blockchain. Peer B and peer C both say, hey, that's cute and all, peer A, but you're wrong, right? That's not right. Now, it might be a little abstract to just look at data and, us typing kind of random stuff in here and think, okay, yeah, that's data, right? That makes sense. Just kind of random strings in here doesn't really do anything for us. So if we actually go over to the token section here, this is where everything really starts to make a lot of sense. So we have the exact same setup here with peer A, peer B, peer C, except the difference is instead of having kind of this data section, we have this TX, this transaction section, right? And this represents all the transactions that are happening in this block, right? So we're sending $25 from Darcy to Bingley, $4.27 here, 1922, right? And it's the exact same thing. So all these transactions are going to get hashed in the exact same way that the data is going to get hashed. And this is why it's so powerful, because again, if I want to be malicious, right? If I want to say, hey, I really wanted to give Jane a lot more money from Elizabeth, so I'm peer A, and I go back and I change it to 100. Well, now, not only does my whole blockchain get invalidated because that was so long ago, but I'm not going to match any of these other chains, right? And so my blockchain is going to be excluded from the overall blockchain. So, and let's go ahead and fix this. And it's the same thing. If down here, if I become malicious and I want to send, I want Miss Audrey to have less money, maybe I want to send $1, and I go ahead and mine it. The same thing here. This hash now, this 2A1 is not going to match peer B's hash of BBA, and it's not going to match peer C's hash of BBA as well. So the two of them are going to say, hey, your blockchain is invalid. It's not matching the majority. You're out, right? So that's really how these blockchains work at a low level. And it all goes back to this understanding this hash idea and using it in this very sophisticated manner to kind of cryptographically prove, where stuff lies.
Now, the way the blockchain works is that instead of random stuff put in this data section, it's actually going to be Solidity code in here, defining ways to interact with different blocks and different protocols that are on chain, or, as we've said before, different smart contracts.
Now, the next question that you might be asking is, okay, well, how do I know? How can I be sure that I'm the one? Let's say I'm Darcy, right? How can I be sure that Darcy was the one to actually send this money here? How do we know that Darcy sent $25 to Bingley? Well, this is where we get into private keys and public keys, and that's what we're going to go into now. Let's just do a quick recap of what we've learned in this section so far, right? We've learned that Ethereum actually runs on this Keccak 256, but we used SHA-256 for this demo. It doesn't really matter. We're just talking about hashing algorithms. So again, a hash is a unique fixed length string meant to identify any piece of data. A hash algorithm or a hash function is a function or algorithm that computes any type of data into a unique hash.
Mining is the process of finding the solution to the blockchain problem. In our example, the problem was to find a hash that starts with 4 zeros.
Whenever a node mines a block, they get paid a little bit of that gas we were talking about earlier for doing so. A block in a blockchain is basically a combination of a block, nonce, transaction, and a previous hash to create this unique hash for this block. And again, depending on the blockchain implementation, this might have a couple other fields or might have different fields, but this is essentially what's going on. Blockchains are decentralized and distributed because many independent users are going to run this blockchain software, and it will check and they will compare against each other to see which blockchains are acting honestly and which ones are acting maliciously. In the blockchain world, majority rules. The nonce here is the answer used or the number used to get this hash. Now, nonce is kind of an overloaded term. It's actually used for a number of different reasons. In this case, we're using it to solve this problem of getting 4 or 5 zeros at the stop of the hash. However, in Ethereum, it'll also be often used as the number of transactions from a given address. So now we're going to talk a little bit about signing these transactions and private keys and some other cryptography pieces, right? Because in this blockchain demo here, we can see we have all these fantastic transactions, right? All these things went through, but how do we know that it was Darcy who was the one to send $25 to Bingley, right? How do we know that actually happened? And this is where all those pieces that we just learned about in our testnet, in our MetaMask account, are really going to start to come to life here a little bit here. So here we have an example of public and private keys. Okay, at the top we have this private key, right? That was randomly generated. A private key is as it kind of states, is a key that you really want to keep secret, because you're going to be using this as kind of your secret password for all your transactions, right? I can really pick any private key, anything that I want, and with it, this algorithm, they're going to use an algorithm. For Ethereum and Bitcoin, they both use this elliptic curve digital signature algorithm. It's a variant of just a digital signature algorithm, and it's going to create this public key, right? I'm really not going to go at all into kind of this digital signature algorithm, but just know it does use some of these some of the hash knowledge that we just learned, combined with some other pieces, to kind of get this public key here. So I'm not going to go too deep into it, but we have this private key that we create, and we get this public key. Now, this public key, we want everybody to have access to, right? This is, whole world can see this. This private key, we really want it to be private. We don't want people to see this. We're going to use this private key as like a password to quote unquote digitally sign transactions. And then people can verify them with this public key. So let's see what this actually looks like. Let's pick a random key, a more secure key, right? Because the longer it is, the more secure it's going to be. And if we go to signatures now, right? Let's say we have this message that we want, right? We'd say hi world, right? We want this to be the message. What's going to happen is this private key that we've created, we can use to sign this data, right? Remember how in the blockchain demo, we were hashing stuff, right? We're using this SHA-256 hash to get this hash. Well, we're doing something similar, but instead of hashing, we're using this digital signature algorithm to create this message signature. Now, what's really powerful about how this algorithm works is that you can create this message signature with your private key, but somebody else can't derive your private key from the message signature. And that's what makes this really, really powerful. However, if we go to verify using this public key, right? And so this is that 0403. This is that same public key. Using this public key, anybody can verify. Oh, let's go ahead and sign it again. Anybody can verify that this signature is yours, right? So you have a private key just for you, so you can sign things, and a public key so that anybody can verify something, right? So anybody can verify this, and let's say somebody tries to fake a transaction from you. They say, "Hey, this is their transaction." All they have to do is verify that this signature against your public key, and very easily this whole thing turns red because it isn't verified, right? The algorithm says, "Hey, that's wrong." So we can go ahead and take that into transactions in this exact same way. So if I want to send money, if I want to send $400 from, my address to another address, using my private key, I can sign that transaction, and anybody else in the world can then verify this transaction, right? And this is why when people say hide your keys, protect your keys, this is what we're talking about. In our accounts here, right? If we go to settings, and again, the only reason that I'm showing you guys my mnemonic and my private key is because this is a dumpster account. I'm going to throw this away at the end of this video, or I'm just not going to put any real money in it. But when we look at our MetaMask here, we have this mnemonic phrase, which allows us to easily get these different private keys, right? So mnemonic phrase combined with, whatever account number will get us a private key. So mnemonic phrase combined with 1, we're going to get this private key. And this is when we look at account details, export private key. Password confirm. This is going to be the private key that we're going to use to sign our transactions, right? This, if anybody else gets access to this private key, they then can sign transactions for us and they can send transactions for us. And that's why we want to keep these private. So it works the exact same way, right? And so this is why it's so important to hide your private keys and hide your mnemonics. Now, your Ethereum address is actually a piece of your public key. Now, to get our address in Ethereum, all we have to do is take this public key that we've created with our private key, hash it using that same Ethereum hashing algorithm, and then take the last 20 bytes. And that's how we'll actually derive to our address here. Now, knowing the exact methodology of how to get the address doesn't really matter because it could change blockchain to blockchain and could even change in ETH2. But just know that that is essentially how kind of these addresses are derived, right? There's some derivative of the public key, right? Because the public key is public, and using the public key in kind of any public way is totally fine, but not the private key. So that is how we sign our transactions. Note though, this isn't how we send the transactions. So this is just going to sign it, create a transaction for us to send. We'll learn later on how to send these transactions. Whew, so that was a lot of information there too. Let's do a quick recap. Your public key is derived by using a digital signature algorithm on your private key, right? And you want to keep your private key private at all times because you're going to use your private key to sign transactions. Signing transactions with your private key, you are the only one who can actually do this because you can't get the private key from a message signature. However, using your public key, anybody can very easily verify that a signature that's signed by you is in fact signed by you. In our MetaMask, our private keys are located in this account details section. You just hit show private keys and type in your password and you'll get your private key here. A quick note here is oftentimes when using your private key somewhere, they want it in hexadecimal form. So if we're going to use our private key for something like Brownie, which we'll go into later, we need to actually append a 0x to the front, but we'll get into that later. And the address of your account is derived from this. So if you think about it, your private key creates your public key, which then can create your address. And there's a little barrier here, or a big barrier here, because your private key you want to keep private, and your public key and your address can all be public information.
Awesome. So now that we know all the cryptography pieces and all the little nitty-gritties of how the blockchain actually works and how our signatures work and how everything sticks together, let's talk a little bit about how this works in actuality and what's really going on. Now, for a lot of this, each different blockchain has slightly different algorithms and slightly different metrics and criteria for doing a lot of this stuff. So when we're talking about these specific implementations, keep in mind the exact algorithm might be a little bit different, but the concepts are all still going to be exactly the same. Hashing and a hash function is going to be the same no matter where you look. A decentralized blockchain is going to be the same no matter where you look. How it's actually implemented is going to be a little bit different. Now, traditionally, when you run an application, be it a website or something that connects to some server, you are interacting with a centralized entity. And unlike how we saw with the blockchain with multiple different peers, it's going to be run by a single centralized group. Now, it still could be run on many different servers, but all those servers are still going to be controlled by the same centralized group. Blockchains, as we saw, run on a network of different independent nodes. When we saw peer A, peer B, peer C, those were different examples of different independent users running the blockchain technology on their own node. Now, when I use the term node, I'm usually referring to a single instance of a decentralized system. So when I say a single node, when I'm talking about a blockchain, I'm talking about one of those peer A's, peer B's, peer C's running that blockchain software. I'm talking about one server running this technology. And again, it's this network, it's this combination of these nodes interacting with each other that creates this entire blockchain. What makes these so potent too is that anybody can join the network, and that's why there's decentralized. The barrier to entry is a little bit of hardware requirements, you getting the correct materials to run the software, and then you running the software. Anybody can join these networks and participate, and that's what makes it truly decentralized. In fact, you can go to GitHub right now and run your own Ethereum node in a few seconds. Now, in the traditional world, applications are run by centralized entities. And if that entity goes down, or is maliciously bribed, or decides that they want to shut off, they just can't, because they're the ones that control everything. Blockchains, by contrast, don't have this problem. If one node or one entity that runs several nodes goes down, since there are so many other independent nodes running that it doesn't matter. The blockchain and the system will persist so long as there is at least one node always running. And luckily for us, most of the most popular chains like Bitcoin and Ethereum have thousands and thousands of nodes. And as we showed in our demo, if one node acts maliciously, all the other nodes will ignore that node and kick that out or even punish it in some systems because they can easily check everybody else's node and see, okay, this one is out of sync with the majority. And yes, majority rules when it comes to the blockchain. Each blockchain keeps a full list of every transaction and interaction that's happened on that blockchain. And we saw if a node tries to act maliciously, then all their hashes are going to be way out of whack and they're not going to match everybody else. This gives blockchains this incredibly potent immutability trait where nothing can be changed or corrupted. So in essence, we can think of a blockchain as a decentralized database. And with Ethereum, it has an extra additional feature where it also can do computation in a decentralized manner. Now let's talk consensus, proof of work, and proof of stake, because you've probably heard these before and they're really important to how these blockchains actually work. When we went through that blockchain example and we did that mining feature, this is what's known as proof of work. Proof of work and proof of stake fall under this umbrella of consensus. And consensus is a really important topic when it comes to blockchains. Consensus is defined as the mechanism used to reach an agreement on the state or a single value on the blockchain, especially in a decentralized system. I briefly alluded to this consensus mechanism in our blockchain example when I said if one changes something and the other two don't, then majority will rule and kick that one out. This is part of that consensus mechanism. Now, very roughly, a consensus protocol in a blockchain or decentralized system can be broken down into two pieces: a chain selection algorithm and a Sybil resistance mechanism. That mining piece that we were doing, or the proof of work algorithm, is what's known as a Sybil resistance mechanism. And this is what Ethereum and Bitcoin currently use. Please note that depending on when you're watching this, if ETH2 is out, then it's no longer proof of work. Now, proof of work is known as a Sybil resistance mechanism because it defines a way to figure out who is the block author. Which node is going to be the node who did the work to find that mine and be the author of that block so all the other nodes can verify that it's accurate. Sybil resistance is a blockchain's ability to defend against users creating a large number of pseudo-anonymous identities to gain a disproportionately advantageous influence over said system. And in layman's terms, it's basically a way for a blockchain to defend against somebody making a bunch of fake blockchains so that they can get more and more rewards. Now, there are two types of the Sybil resistance mechanisms that we're going to talk about here, namely proof of work and proof of stake. Let's talk about proof of work a little bit more in depth first. In proof of work, this is Sybil resistant because a single node has to go through a very computationally expensive process called mining, which we demonstrated earlier, to figure out the answer to the blockchain's riddle of finding that correct nonce or whatever the blockchain system has in place. In proof of work, this works because no matter how many pseudo-anonymous accounts you make, each one still has to undergo this very computationally expensive activity of finding the answer to the proof of work problem or the proof of work riddle, which again, in our demonstration, it was finding a nonce with that first 4 zeros. But again, each blockchain might change the riddle or change the problem to be a little bit different. In fact, some of these blockchains make this riddle intentionally hard or intentionally easy to change what's called the block time. The block time is how long it takes between blocks being published, and it's proportional to how hard these algorithms are. So these problems actually can change depending on how long they want the block time to be. If a system wants the block time to be very, very long, they just make the problem very, very hard. If they want it to be very short, they make the problem a lot easier. We'll talk about Sybil attacks in a little bit and how they can affect the system. But with proof of work, it's a verifiable way to figure out who the block author is and be Sybil resistant. Now, you need to combine this with a chain selection rule, create this consensus. Now, there's some consensus protocols that have more features, but very, very roughly, these are the two pieces that we're going to look at. The second piece is going to be a chain selection rule. How do we know which blockchain is actually the real blockchain and the true blockchain? Now, on Bitcoin and Ethereum, they both use a form of consensus called Nakamoto consensus. And this is a combination of proof of work and longest chain rule. The decentralized network decides that whichever blockchain has the longest chain or the most number of blocks on it is going to be the chain that they use. This makes a lot of sense because every additional block that a chain is behind, it's going to take more and more computation for it to come up. That's why when we saw in our transaction, we actually saw confirmations. The number of confirmations is the number of additional blocks added on after our transaction went through in a block. So if we see confirmations as 2, it means that the block that our transaction was in has 2 blocks ahead of it in the longest chain. Now, I do want to point out that a lot of people use proof of work as a consensus protocol, and I do want to say that this is a little bit inaccurate, but sometimes people use it interchangeably. Proof of work is a piece of the overall consensus protocol, which in Bitcoin and Ethereum 1's current case is Nakamoto consensus. Nakamoto consensus is a combination of proof of work and this longest chain rule, both equally and very, very important. Now, proof of work also tells us where these transaction fees and these block rewards go to. Remember how when we made this transaction, we had to talk about gas and a transaction fee. So who's getting paid? Who is getting this transaction? And this transaction fee is going to the miners or the validators. In a proof of work network, they're called miners, and in the proof of stake network, they're called validators. They are a little bit different, and we'll get into that when we talk about proof of stake. In this proof of work system, all these nodes are competing against each other to find the answer to the blockchain riddle. Remember, in our example, it was to find a hash that has 4 zeros at the start. And again, depending on the blockchain implementation, that riddle is going to be a little bit different. But all the nodes are trying as many as possible to try to get this answer first. Why? Because the first node to figure out the answer to the blockchain riddle is going to get that transaction fee. They're going to get paid from that. Now, when a node gets paid, they actually get paid in 2 different ways. One is going to be with a transaction fee, and another piece is going to be the block reward. Remember how we talked about alternating the gas price or the GUI on our transaction? Well, that's the transaction fee that we're going to pay to these blockchain nodes for including our transaction. The block reward is given to these nodes from the protocol, from the blockchain itself. You've probably heard of the Bitcoin halving before. The halving is referring to this block reward getting cut in half, and it's supposed to be cut in half roughly every 4 years. This block reward increases the circulating amount of whatever cryptocurrency that is being rewarded. For example, on Ethereum, the block reward is giving out Ethereum, and on Bitcoin, the block reward is giving out Bitcoin. So these nodes are competing against each other to be the first one to find this transaction, to be the first one to find the answer to this problem, so that they can be the ones to win both this block reward and your transaction fee. Some blockchains, like Bitcoin for example, have a set time when they're no longer going to give out block rewards, and the miners or the nodes are only going to get paid from transaction fees. Now, this gas fee, again, is paid by whoever initialized the transaction. When we got our funds from the faucet, there was some server and somebody else was paying the transaction fee for us. However, when we sent Ether from one account to another, our first account actually paid some transaction fee to send that Ether. In proof of stake, there's also a gas fee, but it's paid out to validators instead of miners, and we'll talk about that in a little bit. Now let's talk about 2 types of attacks that can happen in these blockchain worlds. Let's talk about the first one being the Sybil Attack. The Sybil Attack is when a user creates a whole bunch of pseudo-anonymous accounts to try to influence a network. Now, obviously on Bitcoin and Ethereum, this is really, really difficult because the user needs to do all this work in proof of work or have a ton of collateral in proof of stake, which again, we'll talk about in a bit. The other more prevalent attack is what's known as a 51% attack. Now, as we saw as part of our consensus protocol, these blockchains are going to agree that the longest chain is the one that they're going to go with, so long as it matches up with 51% of the rest of the network. This means that if you have the longest chain and you have more than 51% of the rest of the network, you can do what's called a fork in the network and bring the network onto your now longest chain. Now, Sybil attacks obviously are when a single node or a single entity tries to affect the decentrality of the network by pretending to be multiple different people, although they're just the same person or entity. And like I said, it's really difficult to do in proof of work and proof of stake. So you can see now that blockchains are very democratic. Whichever blockchain has the most buy-in and is the longest is the blockchain that the whole system is going to corroborate. When nodes produce a new block and add it to the longest chain, the other nodes will follow this longest chain that the rest of the network is agreeing with, add those blocks to their chain, and follow up. So very small reorganizations are actually pretty common when a blockchain picks a block from a different longest chain, puts it on, and then has to swap it out for another block and continue with a different blockchain. However, if a group of nodes had enough nodes or enough power, they could essentially be 51% of the network and influence the network in whatever direction that they wanted. This is what's known as a 51% attack, And it's happened on blockchains like Ethereum Classic, which is not Ethereum. This is why the bigger a blockchain is, the more decentralized and the more secure it becomes. So after you watch this video and you become a blockchain engineering expert, I definitely recommend you run a node as well, because you are going to increase the security of the network as a whole by running a node. So proof of work is fantastic because it allows us to very easily protect against these Sybil attacks and keep our blockchains decentralized and secure. However, it has some drawbacks as well. Proof of work costs a lot of electricity because every single node is running as fast as they can to win this race to get the rewards. This leads to, obviously, an environmental impact. Now, since proof of work and Nakamoto consensus, a lot of other protocols have taken this idea and gone in a different direction with a different Sybil resistance protocol. A lot of them with the intention to be a lot more environmentally friendly. And the most popular one right now is proof of stake. There are some chains that are already using this proof of stake protocol and that are live and thriving. Some of them are like Avalanche Solana, Polygon, Polkadot, and Terra. And additionally, Ethereum has decided to upgrade to ETH2, which will have this proof of stake algorithm as well. It'll also have some other features which we'll talk about in a bit. Now, as a quick aside, all the tools that we're going to learn here are still going to work in ETH2. So depending on when you watch this, everything here is still valid. So let's talk about proof of stake now. Again, this is a different Sybil resistance mechanism. Instead of solving this difficult problem, proof of stake nodes put up some collateral that they're going to behave honestly, aka they stake. In the example of Ethereum 2, nodes put up some Ethereum as a stake that they're going to behave honestly in the network. If they misbehaved in the network, they are going to be slashed or removed some of their stake. Obviously, this is a very good Sybil resistance mechanism because if you try to create a whole bunch of anonymous accounts, then each one of those accounts, you have to put up some stake. And if you misbehave, you're going to run the risk of losing all the money that you put up as collateral. In this system, miners are actually called validators because they're no longer binding anything. They're actually just validating other nodes. Now, unlike proof of work, which every node is racing to be the first one to find the block, in proof of stake, nodes are actually randomly chosen to propose the new block. And then the rest of the validators will validate if that node has proposed the block honestly. As we saw with our cryptography lesson, it's usually very easy for other nodes to verify if a proposal or a transaction is honest. Now, randomness is a really important topic when we're talking about blockchains, because keep in mind, these blockchains are deterministic systems. They're walled gardens from the rest of the world. And as you know, a deterministic system, by definition, can't have random numbers. So how do we choose the random validators in the system? Well, it changes from blockchain to blockchain, and actually choosing the node will change blockchain to blockchain. But in ETH2, they're using what's called RANDAO, at least for the original implementation. This is a decentralized autonomous organization that collectively chooses the random number and collectively chooses which node is going to run next. We aren't going to dive too deep into this because there's a good chance that this might change in the future. But we will go into randomness solutions in blockchain later on in this course. Now, proof of stake obviously has some pros and cons as well. Pros are that, again, it is a great Sybil resistance mechanism and a great way to figure out who the author of a block should be. The other pros are that it's way less computationally expensive to figure out the new block, because instead of every single node on the network trying to do this, only one node needs to do this. And then the rest of the nodes just need to validate it. The cons are that it's usually considered a slightly less decentralized network due to the upfront staking costs it costs to participate. Now, this gets into a little bit of a philosophical battle on how decentralized is decentralized enough, and I think that's up to the community to decide. And as we progress, I think we'll learn more and more about how decentralized is decentralized enough. The general consensus amongst blockchain engineers, though, is that proof of stake is very, very decentralized and very secure. This massive environmental impact improvement is one of the two main reasons why ETH is shifting to ETH2. It reduces the environmental impact by up to 99%. Now, these are the main pieces of proof of work and proof of stake, but I did want to talk about another concept that's really important in these ecosystems, and that is scalability. When we were talking about gas prices, we were saying that the gas prices can get really high if a lot of people want to send a transaction, because a block only has so much block space and the nodes can only add so many nodes. So when a lot of people want to use a blockchain, the gas price skyrockets. This is not very scalable because if we want to add more and more people to these blockchains, it's going to cost more and more to use the blockchains because more people are going to want to get into these blocks. This means that there's kind of a ceiling to how many people can use the system because of the financial constraints that'll get imposed as gas prices keep rising. Ethereum 2 is not only attacking the environmental impact of proof of work by switching to proof of stake, but they are also implementing this new methodology called sharding. And sharding is a solution to this scalability problem. A sharded blockchain really just means that it's going to be a blockchain of blockchains. There is a main chain that's going to coordinate everything amongst several chains that hook into this main chain. This means that there's more chains for people to make transactions on, effectively increasing the amount of block space that there is. Sharding can greatly increase the number of transactions on a blockchain layer 1. Now, there's another term that might be the first time you heard it, a layer 1. We're going to talk about layer 1s and layer 2s in terms of scalability really quickly as well. A layer 1 refers to any base layer blockchain implementation. Bitcoin's a layer 1, Ethereum's a layer 1, Avalanche is a layer 1. These are the base layer blockchain solutions. A layer 2 is any application that is added on top of a layer 1, added on top of a blockchain. Some examples of layer 2s are going to be Chainlink, Arbitrum, or Optimism. Arbitrum and Optimism are very interesting because they are layer 2s that also look to solve this scalability issue. Arbitrum and Optimism are what's known as rollups, and they roll up their transactions into a layer 1, like Ethereum. We're not going to go too deep into rollups and how they actually work, but all you really need to know is that a rollup is kind of like a sharded chain. They derive their security from the base layer, from the layer 1, like Ethereum, and they bulk send their transactions onto the layer 1. They solve some of the scalability issues by being another blockchain that people can make transactions on, still on kind of this base Ethereum layer. Now, they're different from side chains because side chains derive their security from their own protocols. Rollups derive their security from the base layers. So Arbitrum and Optimism, for example, is going to be just about as secure as Ethereum. There's some fantastic guides in there that go a little bit deeper into rollups, and I've left a link in the description for you. All right, so we just talked about a lot of stuff. So let's do a quick recap before moving on. Ethereum and Bitcoin are currently both proof-of-work blockchains that follow Nakamoto consensus. However, Ethereum is moving to Ethereum 2, which will be a proof-of-stake sharded blockchain. Sybil attacks are prevented due to protocols like proof-of-work and proof-of-stake. 51% attacks grow increasingly harder with the size of blockchain, so you should run a node. Consensus is the mechanism that allows a blockchain to agree upon what the state of the blockchain is. Sharding and rollups are solutions to scalability issues on layer 1s. A layer 1 is any base blockchain implementation, like Bitcoin or Ethereum. A blockchain scalability problem is that there's not always enough block space for the amount of transactions that want to get in them. This leads to very high gas prices. And again, gas prices are how much it costs to interact with a blockchain. Whew. So we've learned a ton in this video so far. Everything that you went over is going to make you 10 times better as a developer. Because yes, being a good developer means you understand the code at a very technical level. But if you can understand the overall architecture as well, you can make informed decisions about how to architect your design or how to build your software in however you want to do so. So with all that being said, it's finally time to jump into some Solidity and jump into some code. So let's do this.
So that was lesson 0. That's a lot of information, right? Awesome. Be sure to take this time to take a break and really let the information digest, right? Now that you've learned a lot of these key core fundamental pieces, it's time to move on and it's time to jump into the codes. So be sure to jump into the next video to learn more about Solidity, smart contracts, and start writing some code. We'll see you there.